All right, everyone, welcome back for the last section of Chapter 7. Chapter 7 has two topics. One topic's not really a calculus topic. It's really an Algebra 2 topic that you did in Algebra 2. Might have done last year, too. I'm not sure. Can't remember. But it's a topic we need to solve a certain type of equation that we're going to have in this chapter. So this is called partial fraction decomposition. We throw an integral. I said it's not a calculus topic. It's not really a calculus topic, although you see the integral on there. And so all of a sudden it looks like it's an antiderivative, which it is, but that's the process of how we're going to do this problem. It's called partial fraction decomposition. What we're going to do is break this fraction up into the two fractions that got added together to get it. So there's no other way to do this problem. You could try u sub. I would try u sub real quick. U equals 2x squared minus 7x would be my first thing to do, but du is 4x minus 7, which is bad because it doesn't help me with that. Okay, so this is called partial fraction decomposition. So what I'm going to do is take my original problem and factor the bottom. So you see me factor the bottom is 2x minus 1 over x minus 3. And what I'm going to do is decompose this fraction into the two fractions that ultimately started to get me this problem. So you see I wrote something over 2x minus 1 plus something over x minus 3. And then I'm going to find what these a and b are, okay, that would have given me this equation. So what you see me do here is just a little common denominator stuff. I just multiplied, this term by 2x minus 1 over 2x minus 1, and this term by x minus 3 over x minus 3. So I get a times x minus 3 plus b times 2x minus 1. The denominators are now the same on both sides, so that has to equal x minus 13. What I'm doing is finding a and b. It looks a little bit weird because I got a, I got b, I got x's. The idea here is that a and b are going to be the same no matter what x is. Okay, so you get to actually pick what you want for x and then solve equations. So theoretically, you could pick whatever you want for x. If you pick two different x's, like 10 and 20, you'd get two equations, right? You get two equations that have a and b in them. So let's say x was 10. You'd have 7a plus 19b equals negative 3. Pick another one, you have another one. So you got a system of equations you can solve. But it's not really that complicated because if you choose wisely for x, you'll cancel out one of the variables. So my first thing was I let x equals 3, which means that a times 3 minus 3 is going to be 0. So then I get x is 3, 6 minus 1, I get 5b equals 3 minus 13, negative 10. So I get b is negative 2. And then I do the same thing to try to cancel out the other one. So what you notice what I'm doing, I picked 3 to get rid of that one, and I picked 1/2 to get rid of that one. So now I have my a and my b. So I can go ahead and put my a and my b back in there. And now I have two little natural logs that I'll be able to solve very, very easily. I'm going to stop here, actually, because they're just pretty straightforward natural log questions. All right. So this is a kind of a weird one. We're going to need it, and what we're going to do, it's pretty unlikely you'll see these, but you might see them. Just so you know, it works for any amount of factors, so you could have more than one factor in the bottom. But it only works if power in bottom is bigger than power in top. Notice in this particular problem, my power on the bottom is 2, the power on the top is 1. If not, you're going to have to do long division. You might have to do this after the long division, actually. I think there's going to be one of those in the homework problem you'll see. But if not, you have to do long division to do this. All right, so why do we need these? Well, the big topic for this one is called a logistic differential equation. A logistic differential equation is anything of this form, dp dt. I'm using p for population and t for time, but it could be y and x, could be anything. But typically, a logistic differential equation comes from population growth. So notice in this case, my p is the equivalent to the y, right? So some constant times p times some other constant minus p. The reason it's called a logistic differential equation is because if you graph this thing, it's going to look like this picture I have right here, a little like logistic growth. It goes from concave up to concave down, which we'll talk about in a second. And it actually approaches something. So I'm going to show you how to solve a logistic differential equation. It's really hard. Actually, I'm going to do it right at the end of this video, and I'm going to tell you don't even have to watch it if you don't want to. But I want some of you to see it. It's a really, really complicated process. So we're actually going to give you a general form for how to do it. So what do we need to know about this differential equation? Well, we need to know a few things. So first things first is there is a boundary to this. There's a maximum population. It's called the carrying capacity. And it turns out that it's whatever m is. So if I'm drawing this little picture, that's going to be m. This is called the carrying capacity. It's the limit. Well, that's what I'm going to show you next, actually. It's the limit as t approaches infinity of p, of my population. Okay, same question. Notice my picture is showing that also, right? As we get closer and closer to infinity, my population approaches m. It's called the carrying capacity. Another thing you need to know is that there is an inflection point, because this thing did go from, concave up, notice, to concave down. So there's an inflection point. That inflection point always occurs at half of the carrying capacity. Okay, always have. It's also the time at which the rate is the fastest. Remember, rate is slope of the tangent. Remember, we're going in, let me do that again with a different color. We got tangent, 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 right? So it's the rate at which the thing is going the fastest. So this is a pretty straightforward idea. There's not a lot you have to do. I'm going to show you how to solve it in just a second, but let me just walk you through a problem, because this is what they're going to ask. So they're going to say the growth rate of bears is modeled by this proportion. You, first of all, need to recognize it as logistic, kp times m minus p. Sometimes it's not in the right form. So in other words, sometimes there's like, let me write it this way. I'm just going to make up some numbers here, 100 minus 2p or something like that. Remember, this needs to be a p, right? If you go back to the original form, where is it? Kp times m minus p. So you might have to do some work first. In this case, I'd factor out that 2, which would give me 4p times 50 minus p. So you might have to do a little bit of manipulating. So they're just going to ask the same basic questions. It's a really straightforward topic, like what's the carrying capacity for the bears? Or they might say, what's the limit as time approaches infinity? Or they might say, what's the highest population? It's all the same answer. This case, that's 100. It's the m. They might say, when is the population growing the fastest? Well, remember, the population growing the fastest at the inflection point, which is half m. So it's when the population is half the carrying capacity, which is 50. Now, this is a bit weird because we don't talk about time, right? Normally, when you hear when, you'd want to say, oh, at time equals something, but it's when the population is equal to 50. And then the last question might say, what is the rate of change of the bears when they are growing the fastest? Well, remember that this is my formula for the rate. So I would go 0.008 times 50 times 100 minus 50. I'd probably need a calculator for that. It doesn't really matter, but that would be the rate of change. So that's really all that gets asked in logistic differential equation. It's just kind of new. It's actually a new idea for the BC class. Came into play about 5 years ago or so. Maybe a little bit longer, but we'll study it a little bit more. So I'm going to actually solve one of these equations. So I'm going to start by solving, well, let's do this. I'm going to give you the answer first, okay? And then you can leave and not watch the rest of the video. And then I'm going to do one, okay? You can see how long all that crossed out black, that's one equation. That's solving this equation. It's actually the same Bear equation, dB dt equals. It's just a separable differential equation also, but it's a specifically called logistic because of what it looks like. So I'm going to solve it separating variables. So you might want to watch it. I'll go through it pretty quick. It's not going to take that long. But I'll just tell you right now, in case you want to write this down and move along, that this is the actual solution to the equation. So m over 1 plus a e to the negative, I'm going to write that out so you can see it a little better. Sorry, p equals m over 1 plus a e to the negative. That is the same m. I know it looks a little different there. MKT. And a is some rate. So you would have to find that a And so is K, by the way. K is a rate too. Remember, M is given to us in the problem. So we would also be given some initial condition or something like that, which would then allow us to find the K. Okay, the A's going to work itself out. You'll see as we go through. So I'm going to go ahead and solve one. You probably never have to go through the process I want if you memorize that. I don't think you'll ever see this. I will never test you on this because the process is so long, and I would not expect you to memorize this, although I have seen it on a multiple choice problem in the AP test before. So it's kind of up to you, but it's a long process. So here we go. If you want to leave now, this is not super important, but I'm going to go through it anyway. So I'll go through it pretty quickly. All right. It's a separable differential equation. You can always pause the video, right? So I brought the p's with the p's and the t's with the t's. There are no t's, so I just left the constant over on the other side. It's a separable equation, but it's a little bit harder to solve. It's also partial fractions, which is why we did partial fractions earlier. Notice the bottom is already factored for us, the p times 100 minus p. So I'm just going to walk you through real quick right there. This is me finding A and B. A is 1 over 100 and B is 1 over 100. So I broke it up into the two fractions, 1 over 100p. So this is my A, right? The 1 over 100. It's the A over P. And then this is the other 1 over 100 over 100 minus P equals that 0.008t dt, sorry. Natural logs for both of these. 1 over 100 times the natural log. The 1 over 100 is a constant, just factors out. So the 1 over p is the natural log of p. The 1 over 100 minus p is a negative natural log of 100 minus p, because I would have to do a quick little u substitution there. And then the other side, 0.008t plus c. What you see me doing next is multiplying everything by 100. And there, it's always going to work out that way too, by the way. So I get natural log of p minus the natural log of 100 minus p equals 0.8t plus c. I don't multiply that c by 100. You could, but it's just a constant. It's just another number. So you could call it 100c if you wanted right now, but I just tend to leave it as c. I'm going to combine those logarithms. The natural log of p minus the natural log of 100 minus p is the natural log of p over 100 minus p. So I'm going to combine those logarithms. And then this is where it gets a little bit weird because we know where we're headed. I actually rewrote, I'll show you this intermediate step, 100 minus p over p to the negative 1. So I rewrote this as a reciprocal, and then I brought that negative down. So that's what that negative is right there. Just knowing I did that because I know what's going to happen later, and it's easier to solve. Haven't done anything to the other side yet. Multiply by -1 to get rid of that negative sign. And again, I did not multiply that c by -1. I could have called it minus c, so it's going to work out the same. Okay. Then I exponentiate both sides, e. So I get 100 minus p over p equals e to the negative 8t plus c, 0.8t plus c, sorry. Next step is I broke that up into two fractions. 100 over 100 minus p is over p is 100 over p minus p over p, or 1. Then I added 1 to both sides. And then I inverted and multiplied. So I flip-flopped everything. So I wound up with p equals 100 over 1 plus negative 0.82 plus c. And then I just did my little, remember we did this on these other problems, e to the negative 0.8t plus c equals e to the negative 0.8t times e to the c, and that e to the c just becomes that constant. All right. So there you go. That's it. And then you would be given, in a real problem, right, you would be given some information to help you find the variables that we need. All right. Cool. That's it for that. Good luck with the homework. We'll chat in class tomorrow.